Okay, good afternoon, everyone. It's my pleasure to present you the first speaker of today, Lucie Baudouin, French mathematicians. It's a special pleasure for me because I met Lucie many years ago when she was doing his PhD. And we met in Paris, and since then we keep our relationship, scientific and also friendship relationship. So it's my pleasure. So let me introduce her. Lucie have received the PhD degree in applied mathematics from University of Versailles, Saint-Quentin, and the habilitation dirigée de recherche in applied mathematics from the University of Toulouse in France in 2014. From 2006, she was an associate researcher, and since 2022, she's a senior researcher with CNRS in Toulouse. Until recently, she was a member of executive committee of the International Center of Mathematics and Computer Science in Toulouse. She is currently a member of Scientific Council of the Institute CNRS Informatics. The current research of Professor Baudouin includes stability analysis, control and inverse problem of PDEs. So today she will speak about event triggered control strategy for the stabilization of PDEs. So thank you very much for accepting to give a talk, and you can start.
Thank you very much, Anna. Okay, so I'm going to present what I'm going to talk about, meaning making you understand what is event-triggered control for stabilization of PDEs. And this is very much related to the fact that I'm not working in the Department of Math, but I'm working in a lab, the LAS CNRS, where my colleagues are specialists of automatic control. So if you know a little bit about it, this logo here talks about it. My team group is MAC, M-A-C, and this is a way to present the closed control loop that automatic controllers are working with. Anyway, so I'm going to, that's how it works. To explain to you how we will try to take into account some constraints in the control loop. And the question of constraints in the study of dynamical system is a topic between control theory and information theory, and the goal is mainly to develop methodologies so that we can revisit control problems, taking that into account. I give here some names about a researcher who have been working on automatic control with limited information of various kinds, and I will focus on two specific topics. The first one is I'm not going to work with ODE or finite dimensional system, but with infinite dimensional systems, meaning PDEs, and that's why you should be interested in what I will present. And the second thing is that the constraints I will take into account are concerning time sampling, and they will be explained with the event-triggered control strategy. So our focus here is event-triggered control, and I can give you some references about ordinary differential equation systems, which are these ones, Arzen, Tabuada, and Armstrong, and these papers have been starting to study how it works for systems of finite dimension and to achieve a control task as rarely as possible. This is the first goal, and in a way where, we have to monitor the state of the system to determine the current performance and check if we execute the task as often as needed. Okay, so there is a trade-off between what we need. Concerning PDE systems, you have, okay, I can put that here. You have literature concerning parabolic PDEs, even hyperbolic PDEs of first order. You even have papers about abstract and finite dimensional systems, and you also have works about dispersive PDEs. I don't dig too much into these references, and you can check that if you are interested in that. So now I will start maybe to make things the more understandable as possible with an illustrative example for the damped wave equation, so that you can understand what is at stake here. Then I will present an abstract setting concerning bounded event-triggered control, and then I will give you some hints about boundary control of the waves. So it's increasing difficulty. The first one is just an example. The second one is more abstract, and the last one will be about a more difficult context with boundary control. Okay, so now let's go with an illustrative example. So you take here, for instance, the classical wave equation with a control source terms. U of t and x is the source term of the multidimensional ODE. You have Dirichlet homogeneous boundary data, and you have initial data Z0 and Z1. And you know that if you take U and Z0 and Z1 in the right spaces, then the system is well posed and has a unique solution in the appropriate functional spaces, namely continuous in time, H1 in space, even H1 0 here because we have zero boundary, and C1 in time and L2 in space. If you consider, so I'm not doing controllability, I'm doing closed loop control. So I consider feedback control U of t and x, which is exactly minus alpha dtz. And let's start with this one, the one in red. If I take this kind of control, then I can show exponential stability of the system here, and it is quite well known. I will come back to that later. And here, what I want to do is not taking minus alpha dtz of t at any time t, but decide that I take minus alpha dtz at some time tk, and I stick to this control until a time tk plus 1. Okay, so this is my, okay, two things are named star. Yeah, okay. So I do that. And so the event-triggered control strategy, meaning choosing when the tk update instance should occur so that I can keep my exponential stability. So exponential stability writes this way. You have the energy of the system, which is 1/2 of the norm of the gradient and 1/2 of the norm of the time derivative in L2. And I have this exponential stability. Okay, so we want to keep that result, which is definitely true in this usual case, and which has to be, in a way, true for this situation. So let's see what we can do about that. We have a system that I want to prove that it is exponentially stable, where we have this, let's say, sample and hold control for the equation. And now here is the event-trigger law I'm planning to work with, and I define the next update instant, tk plus 1, as something greater than tk, where I am sure that the distance between the control that works well with the control I'm really applying. Okay, so I'm applying something that hasn't changed. It should have, and it hasn't. And I check that my deviation here is always smaller. I say smaller than 2 gamma e of t. So I take the infimum of the moments where this is bigger than what I want. Okay, so 3 questions occur when you try to do that. The first question is, do I keep well-posedness of my closed loop system? So my system is not only an ODE, a PDE, sorry, but also this event trigger law, and I want to be sure that I have a solution until some time capital T, or maybe until time. The question is the risk of Zeno phenomenon. To check that I don't have a phenomenon where the update sequence, the TK, accumulates somewhere. If it does accumulate, that I cannot time capital T for existence of the solution. And I want to be sure that this doesn't happen. So for just an image about this Zeno phenomenon, it is the situation where you have a bouncing ball that jumps and then the jumps decay and makes infinitely small bounds that accumulates at some point. This Zeno is in another topic, but it's a bit related with the fact that I'm defining this event trigger strategy. And the last but not least, which this is my main way. I had the two other questions coming first. And this work on the wave equation, this specific one, was a joint work with one of my PhD students, Florent Coudaudet, and a colleague of mine, Sophie Tarbouriache. So now let's go to the stabilization on that. Waves, when the damp is minus one, there are a lot of results on this topic. Of technique, the stability, this goes in 79. You also have localized local analysis where you act only on a specific in omega. You have that were developed by on what's the name results. And you also have backstepping Figment design, for instance, from Spilaev and Kristich in the goal of my will be triggered law allows to keep the exponential stability of the closed loop system. And again, I focus on the fact that the sampling is aperiodic. We have a specific law for the next update instant to occur, and I have the Zeno phenomenon too. So now let's accepting. The question is, and what I've presented to you before fits in this framework, but this framework is more general, and I would like to present to you how it works with this general framework. The nice thing about it, you could close the eyes and you could BC as matrices. It is the infinitesimal generator of a C0 semi-group, and B and C are control and observation operators that are like K here. The is close the loop. A plus BKC is still the infinitesimal generator of an exponentially stable C0 semi-group. So last thing I haven't said it. The operator A cannot account for any. It has to correspond to skew adjoint operators, meaning that I have the adjoint A star equals to minus A. Okay, so that's why it corresponds, for instance, to the wave equation that I've presented, but not to the heat equation. What else do I want to say? The way I present everything here is my PDE, my state is Z, and Y is an observation that I make of the state Z, and U is the control I decide to apply corresponding to this that I had as an observation. This is specifically. So now I want to study this PDE system when it is subjected to this time sampling. So now the system looks like that. I have KC, and it goes for time plus 1, and my as before, but in this setting, it's the infimum of the time greater than tk, so that my deviation, the observed one, so c of z of t minus in the, it has to stay a square in the norm or in H, my Hilbert space. And I want to be sure that I have all the time this deviation smaller than this a fraction of the energy of the system. Okay, the same exponential. This work with Sylvain. Refresh you your knowledge about Lyapunov theorem. So this is a converse Lyapunov theorem. It basically says that if I have a exponential, then there is a Lyapunov function to account for that. Okay, so this is technically what it says. I have this operator calligraphic A, which will be my A plus BKC of the previous slides. If A is the infinitesimal generator of a semigroup exponential TA that properties, so it has to be and well, not bounded, but it has to be, we have to be sure that for any Z of the domain of A, the scalar product between then and AZ is smaller than some C norm of Z square. And we have to be sure that A is exponentially stable, meaning that the norm of Z of T is always smaller than a constant M times exponential of minus alpha T. So alpha is my decay rate times the initial data Z0 for any Z0 in H. So if we have that, then there exists a functional, which is a Lyapunov functional, that satisfies these three properties. The first one is that taking V or taking the energies should be the same. It's equivalent to the norm in H, which is written here. In the distribution sense, I have this situation where along the trajectories, the Lyapunov functional is a decaying function of the time. So the time derivative of V of Z of T is smaller than minus 2 beta V of Z of T for some beta, which is completely equivalent to the other formulation below with the scalar product. And finally, I also have the fact that for any Z0 in H, the gradient of V of Z0 is smaller than some constant V of Z0 1/2. These two things are mostly the same. So this, you can find a lot of references explaining this converse Lyapunov theorem, but mainly let me focus on books by Curtin, Svart, or Jacob. And I can also give you some specific Lyapunov functional that proves this right. Okay, you take 1/2 of the energy of this integral here, and this will work to prove all these results. This will follow these properties and make it work. So now I want to take a quick moment to explain what goes on with the three results we need. Okay, well-posedness, Zeno, and stability. So first, well-posedness. The first thing that I have to mention is that we have to define some time that is called here T star. And we'll say that if the TK sequence is a finite sequence, then T star will be plus infinity, meaning we can go to infinity because at some point we don't need to update. The other thing is that if we have an accumulation point of the updates, then let's say that T star is this accumulation point. And my theorem will first say, my well-posedness theorem will first say easily with a basic recursive argument that if I start well, meaning in H, prove the existence of a solution time capital T star. Okay, so this is the first thing I want to prove, but I will also need, for the sake of the proof of Zeno phenomenon, I will need two other things that are important. The first one is written in in red here. It's the left-hand side of my estimate. So if you take the right-hand side here, this part here is basically what you get when you do an energy proof of existence of solution. This is really basic, and kappa here doesn't have a specific sign. It can be positive, and no worries. Here, on the other hand, it's something that says that my solution Z is not crashing to 0 faster than something in exponential minus kappa t. Okay, this is a bit weird. We are not used to write that. Usually we want to be sure that the energy doesn't explode, but here we need to be sure that it doesn't crash to 0, and you will see later why. The funny thing is that proving this or this comes exactly with the same tools. Okay, it's actually the same proof. The other thing I need is to prove some more regularity. So now if I take Z0 in the domain of A, then I can prove that the time derivative of Z is more regular than what I thought, and it has a bound in L infinity in time with values in H norm. And the bound is this one, A plus BK CZ0 in norm in H exponential some constant T star. Okay, and this is an extra regularity property that I need for the same reasons. Quick proof, I don't want to dwell too much on that, but basically you write your closed loop system in a way where you can see why it was working when you didn't write Z dot equal to A plus BKC Z. This is how it should have been if there was not the TK situation, and then you take the deviation on the side. And when you separate the two, then you can study 1 and 2 to prove that, that if you take the time derivative of this energy, well, it can be bounded with respect to the norm of Z. So you separate this term. Here you have the assumption on A that brings you to the BKC scalar product with Z, assumption 1. And then the other term is exactly what it should be. And then you can use assumption to be sure that, well, B and C are bounded, so that you can take these norms that they are bounded. And taking kappa equal to this term, then we get both the two things I wanted to prove my double-sided estimate that is in orange here. Okay, that was easy calculation. I want now to prove that I have extra what is written below here. And for that, I study the system in Xi, which corresponds to the time derivative of Z. And when you take the time derivative, you get this system, which is, well, which is nice because we have some conservation of the equal to A. This is a very basic result. And because of that, you can make this calculation to give in details. So when we do this work, we go from TK to TK plus 1, and then we explain, make it go from one interval to the next one easily. So I don't dwell too much on that, but it's really a recurrence result. Okay, so now my question is, now that I have well-posedness, I want to have a Zeno. And I don't have Zeno phenomenon. The way to prove that Zeno doesn't occur, well, the idea is basically to prove that T star has to be plus infinity. So remember, T star is not plus infinity when I have an accumulation point. So no other way than having T star equal to plus infinity. And this is how it works. We assume that it is finite, and I seek for a contradiction. So remember that the TK converge to T star. So if it's finite, okay, our goal will be to estimate TK plus 1 minus TK by below, so that we are kind of, let us check if there is a dwell time between two triggering time. So I'm looking for this, this dwell time to be sure that they don't. Okay, that's the main rule. So for that, we define, well, we define a function psi k, which is the deviation, the observed deviation. So C of z of t minus z of tk. And we take the y norm square. So what does our says? It says three things. The first one is this deviation is always smaller than gamma square the energy. Okay, this is always the case. This is because of the definition of the event trigger law. Also, this psi k is k plus 1. So when we take t equal to tk, we have 0. This is written here. And when we go to tk plus 1, what is tk plus 1? It's the moment where I reach what I shouldn't. I shouldn't be above that. So when I reach it, it's the moment I update. So in tk plus 1, the limit of this function. Okay? So now that I have that, let us study the time derivative of this psi k. So what we don't want is some time derivative that would be too big. Because if it's too big, I go too fast to my jumping property and I update too often. So I don't want to update too often. I have to be sure that I can derivative. So that's what I'm doing. So I calculate the time derivative in the bound. And well, I have this bound here, which is nice because I know, again, I know a bound on the time derivative of z, I've told you. And if I integrate this inequality, then on the left-hand side, I have this value. This is the jumping value minus 0, which is not here. And I integrate this term. And I will integrate that between tk and tk plus 1. What I do is that I can take the supremum of z, which is here. Sorry, I can take the sup of z dot, which is something I know how to estimate also, and I have tk plus 1 minus tk. So when I watch this estimate here, I can see that I managed to isolate this tk plus 1 minus tk and give some bound from below with all these terms. And the question is, where is my contradiction? Why should there be a contradiction? The thing is that what I assumed was tk plus 1 and tk are converging to t star. So this term, but this here, that comes from all the estimated former theorem, take t star that is not equal to infinity, then I have a bound here that is not 0. So I have here you end weird to you when we colleagues from is that when you are working this event-triggered control, the Zeno phenomenon, the way they rule it out usually is that they prove they have a dwell time. Here we have a, because on the window, and the window is 0. In automatic control, usually does window where we are working. It's a sufficient condition, but it's not necessary. So the way we worked it out here is a bit different, but we understand here that if the window time grows, then the dwell time is smaller and smaller. So we have a kind of accumulation point at infinity. Okay, this is very much related to the work with. Okay, and now we go to the exponential stability. This is what we are, what we were looking for. So now we need the three assumptions. So one was about the operator A, the number 2 was about B and C that have to be bounded operators, and the third assumption, what was it? Maybe I can, we have a glimpse. Yeah, this wanted to be sure that when the system is continuous, then it's okay, it's exponentially stable. So what will work here is, oh, sorry, okay. What, resistance that corresponds when it is that are of the original, and I want to have that I still with a new constancy and a new decay rate. And here you have an evaluation, a precise evaluation of the decay rate that I managed to have. It's not as good as alpha, and it really depends on gamma, which is the tuning parameter of my event-triggered strategy, and depends on K, B, and M, the former overshoot of the exponential stability. So what is the proof? Well, because of assumption 3, so I have access to a Lyapunov functional that makes things work for this. And I will use the same functional for my proof here. So I recall again what is going on here. My deviation term here that I call EK of t in norm is always smaller than gamma square z of t. And this is always true for any t between tk and tk plus 1, so true all the time. I also, so I can calculate what is the time derivative of my Lyapunov functional. And doing the calculations, I managed to prove that what? Actually, I do the same as before. I separate z dot is equal to what it was with no tk involved, and this extra term plus bk ek of t, which is the deviation term. And the idea, basically, I don't want to dig into the calculation, but the idea is that it goes well with this term, and with this term, what could go wrong? Nothing, because I have this energy estimate, okay? So here, what you read is basically, it works well here because my system is the continuously controlled one. So that's why I have that here. And when I'm working with the deviation term, well, I can make some classical Cauchy-Schwarz estimates so that I check that it goes well as well. So I'm using this event-triggered law strongly. Okay, so then here what you can see is that this coefficient here, if you take gamma small enough, you can make sure that this is positive. Okay, and it allows me to prove that I have this -2 delta V that I was looking for. So it's a Grunwald argument that closes the situation where I have proven that V along the trajectories is always smaller than V at the initial condition times exponential -2 delta t with delta positive. Of course, V is equivalent to the energy, and that's why it gives the exponential stability. Okay, so enough with the proof. Now I just want to tell you for the next 5 minutes just some examples and tell you why it is more difficult than expected when we go to boundary control. Well, what I've shown you will work for the wave equation, what I was presenting at the beginning of my talk. It also works with, for instance, the KdV linear equation if you take periodic boundary conditions. We also have results for KdV with non-periodic boundary conditions, but with another way of proving the result. You can also apply this to various systems, but for instance, the Schrödinger equation with localized control in the source term. And you can also imagine other kinds of event-triggered law. So I've just shown you the basicest, the most simple you could think about. If you want to have a look to what it gives, this is how it can be. Here in green, you see what is the initial velocity of the system. And if you apply this initial velocity as a control, then, well, it works well at the beginning, and then it starts following what Z1 is. If you update, meaning that at time 0.05, you update with the velocity at that moment, then you manage to go further. various situations here correspond to various event-triggered law or even to periodic sampling. What is important here to understand is that periodic sampling, for instance, so this is the curves in red here, or here you can see the stairs. The stairs are the updates moments. So when it's periodic, it's in red here. What I don't have is a proof of what is the value of the biggest period that brings me exponential stability. This answer, I don't know how to give. So even if I can find by hand trials and errors that a period of 0.5 is working, well, actually, it's not a proof that I have in hand. And on the left-hand side here, you have, on the left, sorry, you have the continuous control in blue that could be applied to control the system. And you have in dashed line the event-triggered control that is really applied. So it costs less because you don't update all the time. And you change it only when needed, and the result is as good as if it hasn't been updated like that. And I'm going to finish my talk about well, this was about giving other event-triggering laws. The first one here is giving some room about, so we were working with this term only, and we could add some other extra terms to kind of give some room to the update to occur not that often if we wanted. Another strategy is using dynamical event trigger strategy, where you have a dynamical variable m that you use to make the updates for the same reason. You don't want to update too much, so you find strategy to obtain the less you can. And so this is really the last thing is when you think about boundary control, because if you do control of PDEs, of course, boundary control, you know that it is more difficult, the proofs are more intricate, and you are interested in knowing if we could apply this strategy. This teaches derivative domain at some by some control. So you know you can, but there are do that. Gamma 1 have to be specified, and you know that if you take u equal to minus dtz of t times some function of x, then you will have exponential stability. So here the question is, can I put tk and still have it? I take an event-triggered law that is a little bit different from what I've done. It contains some constant term that I need to make it work. And it's an ongoing work with Sophie Tarboriash and Julie Vallin. The idea is that, so this is the setting, the domain omega has to have a hole in it so that gamma 1 and gamma 0 don't touch, otherwise you have problems with regularity of solutions. You have plenty of results proving that it works, and it's kind of well-known material that we teach in a master's degree. But the way you prove that the continuous case, so this case is working well, is quite specific, and it relies specifically on the fact that the domain of your operator contains the information of being equal to 0 at the boundary data, the boundary gamma naught, but also the fact that the derivative, the normal derivative of the first component has to be equal to this kind of domain that information do not allow you to put tk somewhere in it. Okay, that you cannot do. So you have problems with compatibility conditions that are these ones. So the first one is not a problem. You take h1 0 on gamma 0 and it's okay. The second one is tricky because this is where you want to update your control. And this is where the problem starts. And the solution is basically, and the solution, it's not written. That's why I say it's ongoing work. The solution is to do, well, you cannot do that directly. You cannot put tk and say it will work. You have to do something more peculiar so that, well, this is what works usually. If you take that equal to 0, it works. but you're not taking it equal to 0. You take some deviation, okay? This is the EK term of the previous slides. Well, but this is not enough to have that. You have to add two other dynamics. So the deviation term is one thing, but the two dynamics you will add, they will work for you so that you maintain compatibility conditions. And the goal we have is that we mainly finished it, but we can prove exponential decay towards an attractor of the closed loop trajectories of the event-triggered system. And when I say attractor, I'm not towards 0. Well, as I've said, I've taken some event-triggered law that contains some gamma nuts that I need for Zeno phenomenon reasons, and that will prevent me to go to 0, but to some ball around 0. So this is the end of my talk. This was the expectation of proof. I don't want to say more, but I wanted to present you this general result for bounded control operators and unitary PDE operator. This is the framework of my abstract setting. Boundary stabilization is something complicated when you want to do event-triggered control. And other ideas of forthcoming works would be about exhibiting overdamping, for instance, in the waves when we do event triggering. Or we could think about building sampled observers for state or initial conditions in PDE. And of course, consider other types of PDE that don't fall into this framework, but may be possible to event trigger control still. Thank you very much for your attention.
Okay, thank you very much, Lucie, for this very, very nice talk. Let's ask the audience if there are some questions or comments. As usual, you can use chat or microphone. I think you can use also the microphone. So, are there any questions?
I have one question, Lucie.
Okay, yeah, Johnny.
Thank you for your clear talk, and I have liked it. One question of curiosity, because I think that if I have understood well, you have said that when you want to obtain or to apply boundary controllability, the two boundary terms in the domains, the two boundary domains gamma 0 and gamma 1, maybe they have to verify some specific condition, no? And I think that later you said that maybe the intersection has to be 0 or null.
Yeah.
Do you know
Well,
something about that? Or?
when you take when you study the exponential stability, when you study through the boundary, you have to have control on a large part enough of the domain, but because of the regularity of the solution you are needing, them. So here, the more easy way to you can find. I don't know where it is written. I can find it for you if you want, but you can find other ways or other basic drawings of domains omega that still allows to have something that works well with touching gamma naught and gamma 1, but it's specific and you have kind of a spiky point to do that. But the main idea is that you have to control on a large part enough. And yes, that's it. And this drawing here with x0 in the middle of the hole is the good way to represent something that allows this term, this x minus x naught times nu of x, which is the outwards normal vector, this thing to be of the right sign on the appropriate part of the boundary. So this comes really quickly when you study the evolution of the energy. If you calculate the time derivative of the energy, you will find what sign you want for it on which part of the boundary. But then when you want to prove exponential decay, you need more than just the decay of E.
Yes, I find it interesting to know how the domains have to be, yes.
Yeah.
Thank you.
And that's why we have this this problem here. I mean, I've explained the compatibility condition. For instance, just take this one. You need to have the fact that the initial data z0 is equal to 0 on gamma 0, and also that its normal derivative on gamma 1 is equal to this term, so that boundary condition and initial conditions talk to each other. And if you change that at some time tk, even if you start well with z0, z1, when you achieve, when you reach t1, then you are changing the value at the boundary gamma 1 because you want to control not with z1 but with an update of the time derivative of the state. And this update breaks the compatibility condition. That's why we have to organize these extra terms. That the first one is to make sure that we have the first compatibility condition, and the second one is because we want the same compatibility condition for the time derivative of the system. So it's double the work and double the difficulties.
Thank you, Lucie.
Okay, thank you. Other questions? Diego?
I have a couple of questions. My first question is, okay, you have this interval where you have your trigger control, right? It should have any control in any interval like that. I mean, can you have some interval where there is no control acting? Or
Okay, so you are thinking about, yeah, it's another field of research. Here, well, in the proof I have, basically what I rely very much on in the fact that the deviation is not going too far. So and it's monitored by the energy. So if I don't do anything for some time, the question is how bad is evolving the energy. So if you want to prove something with no control at all for some maybe once in a while or every other time, then you have to be able to say something about how does the deviation behave.
okay.
So I haven't thought about it, and I should have a look definitely, because there are a lot of results about on-off control. I can't remember the appropriate keywords, but yeah.
And my second question is also related to that, is about switching control.
Yeah.
I mean, you have that you have these intervals where you have the control acting, and the control acting in some region, right? Some region where it's satisfied some geometrical control condition, and yeah.
Yeah. For the moment, I just need bounded operators, so I just need to be sure. So I can definitely yeah.
So,
do that.
And then my question is that could you have, for instance, in any interval like that, the control acting different part of the domain?
Very good question. I'm guessing.
But I
So
mean,
I
if
will
you look in
I
the
will
whole
not
time,
answer.
you always have that your control is acting in some, but
It comes back to your first question in the end.
indeed,
Yeah,
yes.
but you are right. The question could be different. It could be something like, can I define a bounded operator of control that that says that I'm swapping from one place to another
Yeah,
place?
exactly.
Yeah. Uh, like that, I don't know. I know what I want. Well, I will really narrow my question, my answer, with the fact that if you can prove that your control operator is bounded, you can define it however you want it. So it may be more easy to define this control that swaps from one region to the other one, but you need to be sure that these regions are large enough so that you can control the system, the continuous system. So let me put it another way. The abstract result that I've proved here works with three conditions, and all the three are important. So the bounded is one, and the fact that the continuous control should work. So if you can rely on some paper that proves, even if in a complicated way, that switching control works in a continuous setting, then I can make it work with the event-triggered strategy. Yeah? So I'm answering a little bit on the side, but thank you for the questions.
Thank you very much for your answer.
Okay, thank you very much. I think we are a little bit out of time. So, yeah, no,